This is section 9.10, Taylor and Maclaurin series. All right, so we studied the Taylor and Maclaurin polynomials earlier, and we're going to find out that those are just a piece of a series. So what we're going to do today is look at deriving a power series for a function that has derivatives of all orders. So the form of a convergent power series, and this should look familiar, is that to write a power series, we're going to end up having the series written in sigma notation of some coefficient, a sub n, times x minus c to the nth, which just creates powers of x, hence the name power series. And the center of the series here would be c. So the coefficient a sub n will be the nth derivative of f evaluated at c divided by n factorial. That should look very familiar to you. It's the same coefficient we saw earlier. And so that means that our function is writable as f to the 0th derivative, which means f itself, evaluated at c, over 0 factorial times x minus c to the 0 plus the first derivative evaluated at c divided by 1 factorial times x minus c to the first plus the second derivative evaluated at c divided by 2 factorial times x minus c squared, etc., until you get to the nth term, which is the nth derivative of f evaluated at c over n factorial times x minus c to the nth. And this is where it becomes different from the polynomial of degree n. This continues forever and ever, making it an infinite series. So that plus dot 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 at the end is the thing that makes this a lot different from what we've seen before. So these are precisely the same coefficients of the Taylor polynomials for f at c. Hence, this series that I've written here is called the Taylor series for f at c. Now, let me write that. Taylor series centered at c and then if the Taylor series happens to use c equals 0, this is also, as before, going to be called a Maclaurin, and instead of a Maclaurin polynomial, this is a Maclaurin series. And so those names hopefully make sense because we're using the same thing we did for the polynomials, but we're just making this an infinite series by adding that plus dot dot dot. Okay, so otherwise it should look very familiar and make you feel like, oh yeah, I know how to do this. And I hope you do, because this is something that's not too hard to develop. For example, let's look at a function f of x equals sine of x. And of course, if you take the derivative of this over and over and over again, you end up cycling back repeatedly. After taking the derivative several times, you end up getting the same set of answers. And so this one has certainly has derivatives of all orders, as is required. Okay, so let's do this and find a Maclaurin series. Let's form a Maclaurin series by taking the successive derivatives So the first derivative of sine of x is cosine x. The second derivative is negative sine of x. The third derivative is negative cosine of x. The fourth derivative is sine of x, and then they start repeating in this cycle of four items that are repeated over and over from here on out. I'm going to go ahead and write down one more. It's a good idea to go through about the fifth derivative, just as a general piece of information there. Okay. Then the next thing we're going to do is realize, because it's a Maclaurin series, and that's what the directions say for this one, this means that c is 0. So the next thing to do is to substitute 0 in for c. So we'll be calculating f of 0, f prime of 0. So that c value is replacing the x with 0. So we will evaluate each of the derivatives at c, i.e. at 0. Okay, just setting all those up. Okay, so let's start up at the top. Sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. Sine of 0 is 0. Cosine of 0 is 1. And so not only do the derivatives repeat in a pattern, of course, the substitution of the same c value 0 into each of those is going to have a repeating set of answers, 0, 1, 0, negative 1. Repeat, 0, 1, 0, negative 1, etc., etc. Okay, so now let's write the power series. So the power series will be sigma from n equals 0 to infinity of the nth derivative evaluated at c, which of course is 0, because it's Maclaurin, divided by n factorial, okay, that's our a sub n, that's our coefficient, times x minus 0, which is x, to the nth. Okay, so here we go. So that we'll do the 0th derivative, that is the function itself. Answer at 0 is 0 over 0 factorial times x to the 0. Okay, plus f prime of 0, which is 1 over 1 factorial times x to the first, plus Now put in 2. That'll be the second derivative at 0, which is 0, over 2 factorial, times x squared, plus the third derivative at 0, -1, over 3 factorial, times x cubed, plus the fourth derivative at 0 is 0, divided by 4 factorial, times x to the fourth, plus the fifth derivative at 0, which is 1, divided by 5 factorial, times x to the fifth. And if we stop there, that would be the fifth Maclaurin polynomial. Unsimplified, of course, but that would be the fifth Maclaurin polynomial. But if I add plus ... that means that the polynomial continues and becomes a series. And of course, above the sigma, there's an infinity. So, of course, that's also an indication that it is an infinite series. Then, simplifying 0 divided by 0 factorial is 1. 0 divided by 1 times 1 is 0. The second coefficient simplifies to be 1 times x. The next one simplifies to be 0 minus 1 over 3 factorial x cubed plus 0 plus 1 over 5 factorial x to the fifth plus ... And so this collapses. All of the zeros don't change what we have otherwise, and so they can just disappear. So we're left with x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth. Okay, and what would the next one be? Well, 6 is going to be a 0 again. If you notice all of the even powers up here, with that even power like 0 or 2 or 4, you have a 0 over a factorial times that power of x, and those terms all became 0 and collapsed and went away. So otherwise, the pattern in the derivative answers were 0, 1, 0, -1, 0, 1, 0, -1. So the next one would be 0, right? Then a -1. So that's going to be minus 1 over 7 factorial, because all the evens disappear. Then 0, then positive 1 as the numerator. 1 over 8 factorial. Whoops, I'm sorry. Forgot. Just getting odd numbers here. 1 over 9 factorial times x to the 9th, etc. So the terms of this series alternate, and we have only odd powers of x. X to the first, x cubed, x to the fifth, x to the 7th, x to the 9th. And that is our power series, developed using sine of x. So let's see if we can write a more concise formulation of the series that we just developed. And we'll have n start with 0 and of course go to infinity. And all we want to produce are these particular terms. So realizing that the signs alternate, we need -1 raised to a power. And I'm going to start with n and see if that works out. And I'm thinking that'll work because when I put in 0, -1 to the 0 is going to be 1, which means the first term will be positive. And of course the first x there is positive, so I think that's good. We'll be fine. Then we need to have a power of x that is an odd number. How do we get an odd number if n is 0, then 1, then 2, then 3? Well, you might know this from a prior course. To get an even number, you multiply a positive integer by 2. So 2n makes it an even integer. And once I have an even number, I can add or subtract 1 to make it an odd number. I'm going to add 1 and see if that works out. Putting 0 in for n, 2 times 0 is 0 plus 1 is 1. Is x the first, our first term? Yes, it is. So that's going to work out. And then the factorial in the denominator has the same number used as the power of x. So that also will be 2n plus 1 factorial. And again, if you want to check this out, 0 would give us x, 1 would give us the cube term, and let's check that out. When n is 1, negative 1 to the first is negative, so the second term is minus, correct. Putting 1 in, 2 times 1 plus 1 is 3, so that's x cubed over 3 factorial. I think we've got a winner here. I think this is it. And if we did the ratio test, we would find out that this series converges for all real numbers. It converges for all x. Okay. And I'm going to just state that without going through that. We did some ratio tests in an earlier section, so I'm assuming you could still do that. If not, ask me about it in class, and I can go over it again easily. Now, here's the disturbing part of what we just did. We started out with f of x equals sine of x. And we found its many derivatives and substituted in c equals 0 and developed this whole series. And the disturbing part is I'm not exactly sure that that series would give me sine of x. In other words, the question is sine of x actually equal to this series that we just developed? A disturbing thought to have gone through all that work and then question whether or not it's actually valid. Well, the thing that we do know is that the derivatives at 0 for whatever function this really is equal to, whether it's sine of x or something else, we know that we got the values 0, 1, 0, negative 1, 0, 1, 0, negative 1. Is it possible there's another function that would have the same derivatives as we got with sine, and that's only at c equals 0. That's a single point of which we're doing this. So there's a little bit of angst in me that if we picked only 0, what if we picked centered at pi or centered at 3.7 or whatever number? Is there maybe a function that would have given us different answers, even if fc is 0? Could we have said this is the series? Is this the function sine of x? Is that the only one that could give us this series? So that little ambiguity strikes a little bit of fear in my heart. So if you turn the page, I think you have this slide. I hope you do. It says there could be another function that will agree with the values of the nth derivative of f when x is c and disagree at every other x value. For example, the power series centered at 0 for the function f shown in figure 9.25 is the same series as in example 1. That function being f of x is sine of x if the absolute value of x is less than or equal to pi over 2, but equal to negative 1 when x is less than negative pi over 2, and equal to 1 when x is greater than pi over 2. That would have the exact same series. And so, having done we didn't do it, but we said the ratio test could tell that it would converge for all x. But what does it converge to? That's the question. Does it actually converge to sine of x? or does it converge to something else? Now, it should be obvious that you can't converge to two different things. So it has, for all x, so it has to be some one of the many possibilities. Let's talk about f of x that's defined in that piecewise way up above in figure 9.25. It can't converge to that and to sine of x for all x. It can't be both. So if we have a function f and it has derivatives of all orders in an open interval I that's centered at C, the Taylor series for f may fail to converge for some x in that interval. Even when it is convergent, it may fail to have f of x as its sum. So there's the disturbing part of this. Nevertheless, the theorem that we're about to look at tells us that for each n, the power series that we develop with our stopping at the nth term and then saying the rest of it with plus r sub n of x. Did I skip a page? Make sure I didn't. Okay, no. Where the r sub n of x is defined this way. And this should look familiar because this is what we used before with Taylor's theorem. That it's going to be the n plus 1 derivative of f evaluated at some z, where z is between x and c, over n plus 1 factorial times x minus c to the n plus 1. So that's the part of the series you don't get, that you leave out. And because it's convergent, we know that the remaining part is equal to that infinite series. The rest of it is equal to this term for some number z, where z is between x and c. So there's some number z out there that if you calculated it in that formula to the left, it will give you exactly the remaining part of that series. Now, we can't usually find that z, but we do know that it's between x and c. And a lot of times we can find a boundary, and, you know, like we did before, that we could find that the answer was within so much, like 0.0001 or whatever. So this remainder formula that we have, that value of z depends on x and n. Now, here's the good news. If this r sub n that we've just established what it is equal to, if the r sub n approaches 0, then the theorem 9.23 tells us that the Taylor series for f actually converges to the function f of x that you use to derive it, like it would be actually equal to sine of x. So if this r sub n of x approaches 0, as n approaches infinity, this is no longer going to be in question, and we'll know that that actually is equal to it. So as n approaches infinity, then the series is equal to the f of x used to create it. Okay. So all we'd have to do is prove that r sub n approaches 0 as n goes to infinity. So let's do that for this particular series that we just developed. I want to take away that question mark above the equal sign and show that it actually is equal. And in other words, that f of x equals sine of x converges to sine of x for all x given that Maclaurin series. Okay, so we're going to need to show that sine of x is equal to x minus x cubed over 3 factorial plus plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And it just occurred to me that this is kind of fortuitous. One way to remember that sine of x is x and x cubed and x, in other words, all these odd numbers, is remember sine of x is an odd function. Ooh, wow. That kind of sends chills down my spine. That's kind of cool. Anyway, so we're going to have that infinite, well, not infinite, we're going to have that series up to a certain point and stop at n. And the generic term, which comes from what's behind the sigma up above, would be this. I think I just misspoke. This is not a stopping point. This is just one of the terms along the way in a generic formula to tell you how you produce any term you want, plus dot dot dot. We want to show that that is true for all x. Okay? That's our goal here. Okay. So, now, because those derivatives, there were only 4 answers, sine of x, cosine of x, negative sine of x, and negative cosine of x. We know that the n plus 1 derivative answer is one of those 4 things. Okay, so it's either equal to positive or negative sine of x, or it's equal to plus or minus cosine of x. That's all the possibilities that exist for derivatives of sine. Okay. So, if we thought about the values that are possible and the sine and cosine functions, think about their graphs for just a second. No matter which one of those 4 functions is the n plus 1 derivative, could be any of those 4, it won't matter. But that derivative evaluated at z, which is a number between x and c, is going to be a number between negative 1 and 1, right? That's what the graph of sine of x and cosine of x look like. Then, if we were to take the absolute value of that, that would mean that all of those answers are less than or equal to 1, right? That makes sense. So it doesn't matter what z is. Whoops. Can't talk and write at the same time sometimes. Doesn't matter what that z is. Any real number you pick, if you put it into n plus 1 derivative, no matter which of the 4 it is, and evaluate it, then take the absolute value of your answer, that answer will be a number that's less than or equal to 1 for any real number z that we pick. Okay. So, we know that on the bottom, when we're taking the absolute value of something, it's going to be, the answer is going to be greater than or equal to 0. So 0 is less than or equal to the absolute value of r sub n of x, right? Make sense? And that is, as we've seen, the absolute value of f, the n plus 1 derivative of f, evaluated at z, divided by n plus 1 factorial times x to the n plus 1. Of course, it's x minus 0 because that's factorial doesn't look like a factorial. Put that dot there. Since we developed this earlier, we know that the center is at 0, so x minus 0 is x. Okay. And if we think about that, that would simplify to be, because of the statement right above, that's going to be less than or equal to the absolute value of x to the n plus 1 over n plus 1 factorial. And the reason I can do that is that I can take out that n plus 1 derivative of z that would have been right here. I can take that out and say that that place is less than or equal to 1. And so that means that the rest of the expression would have to be greater than or equal to our r sub n expression. Let me erase that little circle because I know it looks like a 0. It's not a 0. It's the thing we're doing is letting that equal 1, which is the extreme value. That's the greatest number that the n plus 1 derivative of z could be. So we're assuming that it is 1, kind of like a worst case scenario. And anything we get for the expression in the middle has to be less than or equal to the expression on the right. So, all right, then so if we were to take the limit as n approaches infinity of that expression we ended up with, as n goes to infinity, remember that means that x for that limit is a constant. And this limit is going to approach 0 because we know n plus 1 factorial grows way faster than an exponential does. So since that's true, we can say by the squeeze theorem well, I guess I need to make one more statement to make it a completely good squeeze theorem statement. Also, the limit as n approaches infinity of 0 is 0. So we have something that's always less than or equal to our target value, which is this. That's our target value. And that is less than the expression on the far right. So what we've done is the limit of the thing smaller than it or equal to it is going to 0, and the thing that's bigger than it or equal to it is also headed towards 0. So by the squeeze theorem, that implies that the limit as n approaches infinity of r sub n of x is 0. So, consequently, we now know that the Maclaurin series that we created for sine of x actually does converge to sine of x for all x. So this expression we have up here, this is true. We now know that this is true for all x, and we just proved it. I don't want you to worry about having to do this kind of proof. You're not going to encounter much of that until probably a later course where you actually have to do a lot of proving. But it is interesting to know that you can prove it, and it needs to be proven. Now, if you looked at, and I'm going to have to ask you to do this on your calculator, and let me toggle down a little bit so you can see what I'm talking about. Oh, never mind. Well, kind of keep that series up there in your mind. And if f of x is sine of x, so put that in your y sub 1 and make sure you're in radian mode and graph that. Might want to use a zoom 7 window, which is a good, excuse me, is a good window for trig functions. Zoom 7. Then I want you to graph at y sub 2, the first degree polynomial, which is just that first term, and then the third Maclaurin polynomial, which is all the terms up through the term that's got x cubed in it, hence the 3, and graph the fifth Maclaurin polynomial, which includes all powers of x that are part of that series, up to and including x to the fifth, and graph several of these. And you can go further than what I've written. And I want you to see, this is kind of like that e to the x graph that we kept getting closer and closer to as we had bigger and bigger degrees of polynomials. It spread out and kind of matched and looked like it was exactly the same graph as e to the x, and then went away from it, before and after that range of values where it was looking pretty good. This is going to do the same thing, and you're going to get better and better approximations by having polynomials of degree n approaching infinity. So if you were, let me just do a quick sketch of this. Here's sine of x. And if I were to graph, let's do P1 in pink. Well, that looks like when you're really close to 0, it's pretty good, but other than that, it kind of stinks as an approximating thing. If you had x way out here, kind of toward the end of what I graphed to the right, that being approximated by that line, which would be way up there next to the word theorem on squeeze theorem, would be a terrible approximation of it. But when you have a third Maclaurin polynomial, it looks a whole lot better. It looks something like this. And of course, your graphing calculator will do a better job than I can, I promise you. This is very freehand, sort of close to right. And that would be your p sub 3 polynomial. So again, just like the e to the x we saw earlier, the region for which it seems to be agreeing with the function f of x is expanding out. And let me draw one more. And if you're doing this on your calculator, you'll totally get how well it's doing. So this looks something like this. See how well I can draw this. And there's your P5. So again, it's agreeing with the sine function for a broader range of values centered at C. And if you kept going forever, if you could do that on your calculator, it would exactly match the polynomial graph that's infinitely long would exactly match the sine of x. And to me, that's a really cool revelation that you can have an infinite polynomial expression for a trig function, or for any other transcendental function like logs and e to the x and all that. It's really, really cool. All right, so turn to the next slide, guidelines for finding a Taylor series. This just takes you through the process that we went through, and I'm going to do it again with you. So you can read those and kind of have an idea of what you need to do, but I'm going to take you through that process at least one more time. Okay, so let's do f of x equals sine of x squared. Okay, so we find the first derivative. And the derivative of sine of something is cosine of that something times the derivative of the inside something, which we'll probably want to write in this order. Okay, now the second derivative, I notice that what I have now is a product, so I'm going to have to use the product rule. That's going to be first times the derivative of the second. The derivative of cosine of something is negative sine of that something times the derivative of that something. Of course, the chain rule kicks in here. That was first times derivative of the second plus second times derivative of the first. So that would simplify to be negative 4x squared sine of x squared plus 2 cosine of x squared. Remember, I want you to do like 5 or 6 of these. Are you happy with me right now? I'm not. I'm not happy with this at all. This is really nasty. If you want to do the next derivative, feel free. I'm not going to do it. It's really, really getting complicated. And so this is not my idea of a lot of fun. So what we can do instead is using something we already know. Like we know, we've already proven this one actually, that sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus x, whoops, minus, forgot to alternate signs there for a second, minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus dot dot dot. Well, let's go ahead and write the general term. So the general term for that would be that negative 1 to the nth to make it alternate, x to the 2n plus 1 to make it an odd number power, divided by that same odd number factorial, plus dot dot dot. Okay, so that's what we've already proven. That's what we know. So I'm going to claim that because we know that's true, I can find sine of x squared by substitution. So that's going to be x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial plus x squared to the 9th over 9 factorial minus dot 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 plus negative 1 to the nth times x squared to the 2n plus 1 power divided by 2n plus 1 factorial plus dot 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 which simplifies to be x squared minus 2 times 3 is 6, x to the 6th over 3 factorial plus 2 times 5 is 10, so x to the 10th over 5 factorial minus x 2 times 7 is 14, so to the 14th over 7 factorial plus 2 times 9 is 18 over 9 factorial minus dot 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 plus negative 1 times x up to the nth times x to the 4n plus 2. That's when I do 2 times 2n plus 1, distributing, over 2n plus 1 factorial plus dot dot dot, which is way, way simpler than trying to do this using those guidelines. By the time we were thinking about the third derivative of sine of x squared, we were already balking at that idea and saying, no, I don't want to do this. So let's do another example. Let's do f of x equals 1 plus x to the k. And by the way, what we're going to get is something called the Binomial Series. So this is a named series that we're going to produce for this function. Okay. So we're going to find the Maclaurin series for this function, which means, of course, it's centered at 0, and find its radius of convergence. And we're going to make an assumption that k is not a positive integer. That means it could be any negative number. It could be any non-integer number, like 0.6 or something. It can't be 0. That's one we'll have to omit. But as long as it's anything but a positive integer and not equal to 0, it's valid. Okay? So let's do some derivatives. So we have, of course, f of x is 1 plus x to the k. The first derivative of that is k times 1 plus x to the k minus 1. The second derivative is k times k minus 1 times 1 plus x to the k minus 2. Move this down a bit. And the third derivative is k times k minus 1 times k minus 2 times 1 plus x to a reduced by 1 power, so k minus 3. Okay? And let's skip down to the nth derivative. See if we can formulate what that would be. Well, it's going to be k times k minus 1 times k minus 2 times dot 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 meaning we're going to keep going in that pattern until we get to where? Well, for the third derivative, we stopped when it was k minus 2. And for the second derivative, we stopped when it was k minus 1. So this is going to have to stop at k minus, let's see, what would that need to be? For the third derivative, we wanted to take k minus 2, 1 less than that. So 1 less than n. Does that look right? Yeah, that's right. Times 1 plus x to the k minus what? Well, when it was the third derivative, it was k minus 3. When it was the second derivative, it was k minus 2. So since it's the nth derivative, it'll be k minus n. Now, Maclaurin series means c is 0. So let's find some values. F of 0. 1 plus 0 is 1, and it'll always be 1 for all of these. 1 plus 0 is 1. 1 to the k is 1. 1 to any power is 1. Okay? Now, first derivative evaluated at 0. Of course, 1 plus 0 is 1, and 1 to any power is 1. So we'll be left with k. Second derivative evaluated at 0. Oops. That will leave k times k minus 1 times 1, as we've already discussed. And the third derivative evaluated at 0 will be k times k minus 1 times k minus 2 times 1. Whoops, that doesn't look like I drew a 2, like I messed up and made some other number there. Make that look more like a 2. And so if we keep going, the nth derivative evaluated at 0 is k times k minus 1 times k minus 2 times dot 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 times k, distributing, that'll be minus n plus 1. Right on the edge of that, sorry. Kind of ran out of room over there to the right. Okay. So, that would mean that our series would be this. So, the series for that would be f of 0, which is 1, over 0 factorial, which is 1, times x to the 0, which is 1. So that would give us just 1. Plus f prime of 0, which is k, over 1 factorial, times x minus 0 to the first. Remember, it's Maclaurin, so we're subtracting 0 from x. Okay? Plus, then we'd have k times k minus 1 over 2 factorial x squared plus k times k minus 1 times k minus 2 over 3 factorial x cubed plus dot 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 plus k times k minus 1 times k minus 2 times dot 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 times k minus n plus 1 all over n factorial times x to the nth plus dot dot dot. Please make sure you add that plus dot dot dot, which makes it a series. Otherwise, it's a polynomial. By the ratio test, we could conclude that the radius convergence is 1. I'm not going to go through that. You could do that if you want to as an exercise. But the radius convergence is 1. So the series converges. The series converges. Oops. On the interval centered at 0 that goes from -1, which is 1 to the left of 0, to 1, which is 1 to the right of 0. I forgot to write the word 2. Oops. Converges 2. Or, no, that's not right. 4 is actually better. Let me just erase a bunch of stuff and make it look right. Series converges in the interval. That's actually the best word. In the interval -1 to 1. Now, this is not done as using a geometric series idea, so we could not conclude anything about the endpoints from, geometric, we don't test the endpoints. But this one was not done that way, so you need to test the endpoints. And actually, you would need to test the endpoints depending on k. You may or may not include one or both of those endpoints. So it really depends on the value of k. So if you have a problem like this, you'll have to use that particular k and then test the series at the endpoint when x is -1 and when x is 1. And like I said, sometimes they'll be included, the endpoints, sometimes they won't, or one will and the other one won't. So you do have to test that. All right, I'm going to stop this for now and go to another part of this series of videos.